All right, guys. So the big concept that I really want to explain to you today, it's a fun one, and it's really related to what you have already learned in the past. Once again, just like fields and forces, yeah, you did that before with the gravitational force. So I bring in the electric force and say, hey, they are the same. You already familiar with the gravitational field, so I brought in the electric fields. The concepts are the same. So now it's our turn to introduce to you potential. Okay, and you have already heard about this word potential, which is gravitational potential. So I am going to bring in the electric potential into the picture, and you can guess the concept stays the same. Okay, sounds cool. All right, by starting like this, then I think you can expect that things are supposed to go very easily now, except, all right, we always have some exceptions, because we have already seen that the business in electric is more complicated, because you have two types of charges, right? You have positive charge and you can have negative charge. And the force or the field that these charges are generating can be in the outward direction for positively charged particles, or towards the charges in the case of the negatively charged particle, right? So you have sort of extra things to consider. In contrast to gravity, you only have like gravitational pull. There's no pushing, right? It's only pull. All right, so same thing will happen here. Because of those two types of charges, then electric potential, it's going to have the same concepts, but all right, there'll be a couple of things that you have to consider a little bit, right? Because you have to take care of the pushing and the pulling stuff. Okay, so you have sort of something that will have different or opposite effects. Okay, so what I'm going to show you today is what does it mean by electric potential. So we're going to take a look at the definition. Okay, and you might be wondering in the next slide, Ajahn, there is electric potential energy. All right, and this is the weirdest stuff. These two looks to be the same, but they are not. There's no sound effects here today. All right, so these two are not the same. The missing part of this one is you don't have any word of there's no energy at the end, but this one has an energy to it. And you will learn today these two are related, okay, very close, but they are not the same. Sorry, they are not the same. All right. So what we will show you is what does it mean by just the word potential. You have already learned about this potential energy, mgh. That was fine in the gravity. Okay, but what does it mean by just pure potential? All right. And if I can get these concepts of these two things across today's lecture, I think I'm okay. All right. And then we're going to leave this relationship between the electric field and electric potential for next time, because this last portion of this slide is going to be something related to calculus one more time, which I don't think you guys like it that much. All right, guys. So let's dive into this one. All right. I'm going to have to talk a lot today because, I mean, once you get the concept, I think the way to calculate things are quite, I would say, straightforward. Okay, but I think the most confusing part is understanding the underlying, principle of how to define electric potential and electric potential energy. Okay, all right. So I'm going to start like this, guys. So think about this. I'm going to have to compare with the gravitational potential energy just like before, right? So once again, I have my mouse right here again. Okay, so you have gravity pointing down. Okay. So I grab this mouse, bring the mouse up. So that means I'm going against the field. Everyone with me, right? I'm going against the field. The field is pointing down. I'm pulling this mass against the field. But everyone know, if I bring this one up, and the distance that I brought this up is h, everyone can answer me right away. If I take my hands down here at the bottom of the screen to be my reference, and everyone can answer right away, what is the gravitational potential energy of this mouse? You guys, what is it? mgh. Good. And it's mgh above the ground. So it's a positive mgh. I can let it go. It dropped down to the floor. So it get back down to zero again. It's a concept, right? So that's it. So what you did was, I mean, if you think in thermodynamics way, my hands is the external force. This, I'm somebody else, right? Your system right here is the mouse. So there is an external force acting on this mouse, pull it up. So that means I am transferring energy to the mouse. You guys with me? The mouse right now is sitting, at 0 level, so it has no energy. And then there is me, which is external. Grab the mouse, do some work. Work means energy transfer. So when I lift this mouse, I transfer my energy from my body to the mouse. So at the end, the mouse has higher energy. How much? mgh. Cool. It's that easy. That is easy. So how much work do I do? Of course, if I do it in the equilibrium manner, all right, I have to pull my hands up with the same amount of the mg that I pull. I think is pulling it down, correct? So that's why I'm grabbing the mouse, pull it up with the force mg, and I drag this mouse up by the distance h. So how much work do I do? It's mgh. That's it, guys. That's the end of today's lecture. No, I'm just kidding. Sorry. That's what it is. The potential energy is what? The potential energy is the potential energy. So it means it's the potential that this system about to do something. It has ability to do something. What does it mean? It means if I can let it go, it's ready to move down. So it means at this configuration over here, it has potential, it has energy in it. So it's ready to release that energy and do something. Cool. All right. So that's what this one is. So the same idea. So what you really want to calculate is, it depends on how you approach this one. I approach it from the external force. But then you already learned from thermodynamics, there are only two sides of the story. It's either external or it's just the system, right? It's your choice. Okay. But the good thing about this one is we can erase the whole idea of gravity. And then you can think of this one as an electric field. Cool. All right. Stick with me here. All right. So stay with me a little bit here. So let's say if I have right now that the gravity is being erased now, and I replace it with the electric field that is pointing down. Cool. And the mouse is being replaced by a charge. Let's say this mouse is just a charge particle with the charge Q. So the charge is sitting here. Electric field is pointing down. I am come in and grab this charge, bring it up by the distance h, just like before. So what do you think will happen? Yeah, you say, all right, now the charge has potential energy. And because this is a potential energy under electric force, so we're going to call this electric potential energy. All right, it's supposed to be like a big clap in your hands right now. That's it, guys. Okay, so same concepts are exactly the same. And you're already familiar with the potential energy. We're going to still define it just like before. And if you really want to speak in terms of like the equation that we did in thermodynamics, of course, the work done by the system, right? If you talk about by the system, you just have to put the negative sign on, right? If you don't want to put the negative sign on, that's the external force. It's the one that I just showed you. I am the one who grabbed this and then bring it up. So, and that's it. It's going to be equal to the change of the internal energy, because right now you are not talking about kinetic energy. So the only thing that's come into play is going to be now potential. All right. So that's a whole sort of like give you an overview of what is about to happen. So here we go, guys. So look at this diagram. This is exactly what we just did. So start from here, you have electric field pointing down. Okay. And you would like, now let's do something natural here. If you have a particle at point A at the top, and then you say you want to move this particle from point A to point B, how much work is going to be done by the system? Okay, let's give it a shot. By the system now. So that means you let the system perform things by itself. Okay, so let's see if you can follow my thought now. I'm going to switch, the role a little bit here. There's no external force. I'm not grabbing this particle anymore. Just let it go. So right now, You look at this one, Ajan, that's easy because if this one has a charge Q and is under the electric field that is pointing down, it will experience the force QE. Is it cool? Very nice. All right, we learned that one. That's force and the field. And then it's travel by the distance of D pointing down as well. So what I'm saying over here is, so that means the work done by the system, so let me emphasize on the system, is just going to be QE, the force, dot with the displacement vector S, it's a F dot S. And in this case, your vector S is just the distance D. So it's going to be QED cosine 0. And that is just QED. Is it cool? All right. And from thermodynamics, we just say the work done is going to be the negative change of the internal energy of the system. Yeah, we have the negative sign because this is a work done by the system. So what you have over here is going to be negative the internal energy at the final minus internal energy at the initial. The final point is B, initial point is A. So at the end, it's going to be UA minus UB. So what does this equation saying? It's saying that the energy at point A, subtracting the energy at point B, there, what you're going to get is you're going to get to be equal to mg, oh, sorry, not mgh, sorry, QED, and it's positive. And this is a conclusion why you will have to answer, I mean, you have to say exactly the same, that at A, it has a higher energy than at B. Because of this difference over here, U sub A minus U sub B is positive. So it's saying that U at A is higher. Is it cool? All right. So at least this is something that you can summarize based on the comparison to the formula. In gravity, mgh, you change m to q, you change g to e, you change h to d, the formula look exactly the same. All right, and the way that you understood before with the gravity works here. All right, but anyway, just to write things down in a more proper way is just that you have to say is the du, which is talking like in terms of calculus over here. So what you say over here is the change in the internal energy is a negative change of the work done by the system. And the work done by the system is just a force times the displacement. Or you do it calculus way, but you don't need it right now at this point because E is just constant pointing down. But we want an expression. So if you want the total change, you just do the integral of this whole thing. Okay, so this one just in case that you have to face with a very, very general, uneven, non-uniform electric fields on, and the displacement is not just a straight line. Okay, you can use calculus here, but at the end, this is what it is. There you go. So the change of the potential energy is the negative. So I hope everyone understand what does the negative sign. It's in now because it came from thermodynamics, if you think it that way, or it came from the idea that you have to take care of the direction of the force that you are talking about, right? If you talk about the system, you have the negative sign. If you talk about the external force, you don't have the negative sign, on and on. All right, but over here, this is the formula for you to calculate the potential energy change. วันนี้อาจารย์พูดรู้เรื่องเนี่ย Is that still okay with me so far? Give me a second here. All right, so that's what it is. All right, okay, so good. All right, don't worry guys, toward the end it's going to be easy. I know this is annoying because the concept of potential is annoying in a sense that it's just like takes so much time to explain, but the final point is very easy in the sense that the calculation is very straightforward. So just, bear with me the first half of the lecture today. Okay, now here comes the electric potential. All right, what you had before was just like, there's no difference from gravitational case. They all look exactly the same. Okay, it's the same concept as the gravitational potential energy. But now we have electric potential. The word energy that just disappeared. Can you guess what is happening here? All right. The concept of this one is, I think I just guessed physicist's mind back in the history over here, that it turns out what we are learning in electric has a major difference from what we are learning in mechanics, in the sense that you don't have a single object to follow. That's that's sort of like my sense of it. So when you were looking at the Newtonian physics, you have a mass, right? M. And you can pretty much like follow this mass. This mass can do anything. You can throw it. You can, move things. You can do oscillation, blah, blah, blah. You have a mass that you can pinpoint where it is, what kind of object. But think about electrons, proton, charged particle. I don't think you can put a tag on it and just follow them. Right? There's no way. Electricity that you use in household, you don't even care which electrons you're using. And you don't even care. You want to follow it, any particular electrons, and you want to see how it goes, So that's what it is. So in electric, electron, proton, all the charged particle, it's just crazily big amount of charge. And you cannot even distinguish them. So it's going to be tough for you to talk about one particular piece of charge. So they have to let that one go. How to let that go? You have to do it per Coulomb. You guys with me here? So think about this one. If you learn Newtonian physics and somehow you cannot distinguish all the masses that you have in your system whatsoever, all the masses look the same to you, you probably don't want to define mass in the first place. And all you need to do is just, okay, let's do it per kilogram. And later on, whenever you have a mass that you have 10 kilograms, you just multiply by 10. If you deal with 100 kilograms, you multiply by 100. You get that concept, right? So that's why in the electric, you don't have that, sort of like a mass that you can follow. Let's do it per Coulomb, Majan. And then at the end, how many Coulomb you are talking about, then you just use this one and multiply by that amount of charge at the end. And that's it, guys. Concept is very simple. Electric potential is defined as the potential energy. That's what we had. And then you divide it by the magnitude of, they call it the test charge again. But we already discussed about this when we were talking about the field and the force. Whenever they talk about the test charge, think of it of 1 Coulomb. Just make it disappear, right? It's just a bam. What happened with 1 Coulomb charge? That's my test charge. So that's good. The good thing about this one is you don't have to worry about the Q. You only take the Q to be number 1, which is 1 Coulomb. So the formula that you had before, you can imagine like you just move Q to your left-hand side. So it's a change of the energy per unit charge. And that we're going to define it as potential electric potential. That's it. And we use the symbol V for that. So in your head, this is very easy, guys. There. See? V, potential, is just U per Coulomb. Done. And look at the formula. How nice and neat is this one? It's neat. You don't have any Q to worry about. So what does it mean? It means by just knowing the charge, and you know how far away you want to compare between two positions inside that field, you can calculate the potential difference right away, guys. That's what the words mean, potential difference. And I think you know this one already in everyday lives. The unit of this one is joule per Coulomb, and joule per Coulomb is volts, guys. So your household electricity using like 220 volts, that's it. That's a potential difference. So now you understand very easily that it means when you want to jump across the connectors in your household, right? It's 220 volts. So that's 220 volts. Every time that you have 1 Coulomb jumping across that, you already use up 220 joules. Is that easy? Make sense? All right, because 220 volts is 220 joule per Coulomb. That's it. So how many Coulomb you want to have electron jumping around You just multiply by 220 and you get the amount of energy that you are consuming. Isn't that cool? All right, that is it, guys. So that's why this one is so important in the sense that it's the one that we are using every day. Volt, we're using it right now. Okay, try again, guys. So jump right into this one. So I hope by this time you see the comparison between the two. It's kind of like it's departing a little bit because we have no definition of gravitational potential. No, usually we use potential energy, right? But for electric, we have extra definition of the potential. You dropped the word energy. Okay, cool. All right, and the good thing about this one is, see, so the formula is actually more compact because you don't have to worry about the charge anymore. You can just look at the fields. See here. See, you can just eliminate all those charges. And then when you look at just the field, you just get a sense of what it is. Like Ajahn, somewhere around here and somewhere around there, you can tell this one is low V and this one is high V. Can you see what I'm getting at here? Because electric field is pointing in the direction of higher potential. Does that make sense? Oh, I'm sorry. I'm going backward. Sorry. My bad. Okay. So it's high V. Sorry, my bad. It's a low V. Oh, you just got confused. Ajahn, that's what it is. Okay. So the reason for that is because you can compare this with the gravity. The gravity is pointing down. And every time that you look at along with the gravitational field, you're going from high U, right? We didn't have V in the gravity, to the low energy, gravitational energy is pointing down, right? But the good thing about this electric field is, whenever you have electric field pointing down, you know that it's pointing towards lower potential. Okay, so that's what it is. So you can pretty much analyzing just the field alone, and you can be able to direct whatever you're understanding towards potential by knowing the connections between the two. Okay, sounds like not too bad, I hope. All right, so anyway, we'll still look at more. All right, just to make sure that you understand what is going on here. I'll have another example over here. Let's look at this scenario now. So let's move on from pointing down. The reason I want things to point down because we can compare with the compare electric with the gravity, right? But now let's say electric field can point in any direction. It can go crazy. So electric field point from left to right. Okay. And now let's try the case when your displacement is now not in the same direction as the field. Make it a little bit more complicated here. So let's start from point A. And let's say you move to point B through the displacement vector S. The question is, what is the potential difference between point A and point B? Okay, all right, so I'm going to show you right here. So everything will go back to this expression over here. That's it. By definition, the potential difference from A to B is just a negative, the integral of E ds. All right, the negative sign now, you kind of get it. The negative come from when you go against the field, you're going up the potential. Yeah, you're going higher in potential. So that's why you have to have a negative sign over there. So I'm going to show you here. I'm going to calculate the potential difference from A to B. It's a negative E dot ds integral from A to B, initial point to final point. So far, so good. But now the E is pointing horizontally. The ds is just a tiny change in the s. So you can think of ds is just this. There you go. It's a tiny vector pointing along the displacement vector. You slice it into a tiny piece. So at any moment in time, here, the E is pointing horizontally, the ds making theta angle to it. So what you can do is over here, about Ajahn, this is not hard, is the E ds cosine theta. With me, guys, from point A to point B. Okay, now, cool. But the good thing about this problem is the theta is a constant. The E is also a constant. So that means I can pull those two out in the front. So it's going to be E cosine theta and just the integral of ds from A to B. Cool? So far, so good? Okay. And by doing this, you don't need to integrate anything because the integral of the ds, you get the whole length of this vector out. That's S right there. With me? All right, just keep going. So what you have over here is going to be negative E. This whole thing give you just S. Don't have anything different than before. So it's S cosine theta. With me, guys? Okay. And that's the end results over here. But then you notice, Bajan, S cosine theta, it's just D. So actually, I can say it's a negative ED. Woo! You with me here? I know you just like, what is going on today, right? So many things going on here. But all right, just tilt your head 90 degrees. All right, and make your electric field pointing in the downward direction, just like before. Do you feel anything here? It's nothing different than I start from A here, all right, and I just move my mouse instead of moving down. I just move in the diagonal fashion, or I mean, just make some angle over here and place it on the floor. No difference, right? If you turn your hands, like, okay. So that means it doesn't matter where I land as long as my final position is on my blue dash line over there, the potential difference will all be the same, right? Is it good? Yeah, just tilt your head 90 degrees. You will see what I'm saying at. And not only that, but Ajahn, you're not only starting from point A, as long as you're starting at anywhere on that level on the left, blue dash line over there, and you stop on the second blue dash line over there, the potential difference are all the same. You guys start to see what I'm at right now? Yeah. So it's just like every time you have electric field, you can cut those electric field perpendicularly. That will give you the level of the potential. Just like right now you have gravity pointing down. You slice the gravity horizontally, that is your height, that's your level. You slice on the ground, that's your ground zero, and it's ground zero. So that's a zero height level. You slice as 1 meter, so that's 1 meter height. So you can move a mass from 0 to 1, no matter where you move, they're all having the mg1 difference in potential energy. You got that one? All right, so same thing over here. So I think now you see a little bit of the relationship between the electric fields and the electric potential. The potential is just a number. It's trying to give you the level of the potential. And if you take that potential, multiply by the charge, you get the potential energy. Whew. All right, I hope this works. All right, and that conclusion that I have is you can go from anywhere from here to there. You can go diagonally here. You can go crazy all the way, come back here. They don't matter. At the end, you will have exact same potential difference. Because, come back to the first page over here, electric force is conservative. When I say conservative, what does it mean? It means it doesn't depend on path. I can move my mouse up straight, zigzag, curve. I can go diagonal. Doesn't matter. My energy changes, they are all mgh, independent of path. Because the electric field had the same characteristic as a gravitational field. So the potential will have the same characteristic as well. It's path independent, guys. So that's it. So I don't care. You care only the starting point and the endpoint, you will be able to calculate potential difference, or if you want, potential energy difference. พอรู้เรื่องไหมเนี่ย All right, I hope it works a little bit. All right, it might not be at the best setting describing this. All right, but I think it's get you somewhere. All right, here we go. All right, and this is the annoying part. All right, and this is where the complication comes in. We start to do this, sort of like we're going to jump from this definition over here that you saw. You don't like that much anyway. This equation is an integral sign with the dot product in there, with a negative sign in the front. And then textbooks still bring you further to do something about potential around a point charge. All right, this is an annoying one, seriously, because I used to try to explain this slide and it took me like half an hour. The reason is not because of the complication in the definition of the fields and the force and the potential and everything. The complication comes in with the coordinate system. Yeah, remember guys that we were talking about in electric fields and everything, we have to use this spherical coordinate. That r hat is annoying. Seriously. All right, so instead of going through this vector calculus proof and all this stuff, I just want you to think in the analogous way what you did with the gravity. Just one more time. Just one more time. But now let's zoom out. We are not on the surface of the earth anymore. We are in the outer space. Okay, so what will happen? So now I have a charge Q right there. Everyone still remember that the charge, if this charge is positive, it will generate electric field pointing outward, right? So let's do that. So electric field, it's too thick. Electric field will point outward, 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 out, 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 out. Okay, cool. So far, so good. And we just learned that every time that you have electric field line, if you cut through that line perpendicularly, you will get the level somehow. Get a level. Or if you think even more primitive than that, if you go along with the field, you are going toward lower potential. You guys with me here? So what this direction of the electric field that is pointing out is trying to tell you, it's telling you that when you go further away from the charge, you are going toward lower potential, which makes perfect sense. If you think of this one as Earth, yeah, when you go further away from the Earth, you will feel less and less gravitational pull because you're so far away from it. All right, and the decisive parameter that tells you how big is your pull from the gravity is how far away from the Earth you are. And you only care about the radius. You don't care about the orientation, or I mean, you don't know, you don't need exact position of yours. You only need to know how far away from the Earth. You can be at any angle, any directions from the center of the Earth, you will feel the same gravitational pull. So that's why the key factor that will determine the potential when you are away from the charge is just the radius, the distance r right there. Does that make sense? And now you kind of know that further away from this, the bigger the r is, the smaller the potential. And the direction is radial, in the radial direction. So it doesn't mean, it means you can be at any position at the same radius. For example, if I talk about this inner circle over here, so you can stand on any point in this, on this green sphere. Think of it in three-dimensional. And you can move from the green sphere to the orange sphere, right? Your potential difference will all be the same. What does it mean? If I start from here, I can end up there. I can start from here. I can end up here. I can start from there. I can just move around, end up here. I can start from here and then can just go crazy and then move up here. Doesn't matter. As long as you're starting from the green and you end on the orange sphere, the potential difference, they'll all be the same. because of the path independence property. Plus, you know that the potential only determines by how far away from you from the charge that's generating that potential. Does that make sense? Does that help? All right. So instead of proving this, I give you this formula right away. And the way that you can calculate the potential from a point charge Q is by doing the KQ over R, and that's it. You are done. Sound effects here. All right. All right. And that's good. The good thing about this one is it's a scalar quantity, guys. So you don't have the direction to worry about anymore. You only care about how far away from the charge Q you are, and then you can calculate potential right away. The only thing that you have to concern a little bit is when it's a scalar, it means it can have positive, negative value now, because positive charge will generate positive potential and negative charge will generate negative potential, right? Because now we have push and pull effect from the two types of charges. So potential will do different things as well. Okay, one will do the pushing, one will do the pulling and all this stuff. So you have two types of, well, the value, let's say the value of the potential can range from negative to positive now. Okay, and I will show you exactly how can we utilize this formula to calculate the potential from some problems that we're going to go through together. But you guys okay with this? Sound like it's more like a hand waving, but I think it's just faster for you to just grab this one and, utilize it. And then maybe later, if you really want how to get to this formula, then you can just come back and read this slide one more time. All right. But yeah, for majority of you guys, I think, yeah, just take this one and use it. I think that's better, I guess. All right. So that's one thing that we have on our hand right now. So that's it. So this one gives you a conclusion of what does it mean by potential from a point charge. Now, one final annoying part, guys. Okay, the conservative force nature of the electric fields checked, no problem. The independence of path checked. So if you have a closed loop movement, there will be no potential difference checked. You guys with me? One more time, just to confirm. You start a mass here, you can move up and then come back. That's a closed loop. When you have a closed loop, nothing has changed. Potential doesn't change. Potential energy does not change either. So no change, zero change. Cool. The only thing left is this. When you consider this one, point charge generating the field radially outward. But every time you talk about potential, and you have been taught this forever, every time you talk about potential, you need a reference, right? Like we do this, okay, I'd say, hey, the bottom of the screen is my reference point, that's 0 height, and then you do mgh. H is the height relative to this reference point. So what done? So if you have KQ over R, where is your reference point? Because potential must refer to, relative value to something, right? So that's it. The potential is taken to be 0 at a very, very far away. This just to make things, perfect in terms of the definition of everything that we have, defined and used for potential. The one thing about this one is it's getting sort of like a lot of stuff going on over here, but just want to make sure the reason that they need this one is just, how can I say it? Just to make it in the sense that everything is still well defined. But in reality, every time that you trying to work with potential, you always do potential difference. You will notice that later. But if you really want to talk about one single value of potential, usually it will mean you already compare it to your reference. Does that make sense? Okay, give me one more time. How about this? All right. If I bring this mass up and I'm asking you, well, hey guys, what is the potential energy of this one? You guys may be saying, yeah, John, mgh. But by using that edge, you already assume that is the height with respect to some reference. Because your friends just came in, maybe just say about John, your potential energy at this point is 0 because I draw the line at the top of my screen to be my 0 height. That's also possible. Does that make sense, guys? So usually when you want to talk about the absolute value of potential, it doesn't seem to make a lot of sense if you don't have any reference, because everyone can reference at any point. It doesn't matter. They can pick their preference and then they can set everything to 0 all the time. So that's why for this one to have like, you know, a single formula that can be used to give you the sort of like an absolute value of the potential, it must mean there's no absolute value of a potential. It must be the value with respect to something all the time. And that's why for you to be able to use this formula to tell everyone that, hey, this is my potential from a single charge particle Q at a distance R, you already imply that you set potential to be 0 at infinity. That is your reference. That's it. The reason I said that's it because it's an annoying one that you have to have that clause saying that, hey, potential is 0 at infinity. So you will be able to use this formula. That's the whole point. Otherwise, then it's kind of like it's wrong in principle. It's incorrect. If you want to use this formula without referring to 0 at infinity potential, then it fails from the beginning or something like that. All right. So to me, let's think of it this way. Every time that you see this line over here saying that, hey, potential taken to be 0 at infinity, that is your ticket for you to use this formula. That's it. Okay. So that's the whole point. The point is, okay, when you see that line, okay, I'm safe to use V equal to KQ over R to calculate potential from a point charge. Okay, guys, that's my conclusion. All right. Okay, maybe the whole explanation that I have for you guys is kind of like, what is going on? The reason is because it's a huge concept to take, right? The potential. And I know I hate this one. I hated this first time I saw this one because so many things going on. So for those of you that don't really like what I just told you in the past 50 minutes and all this stuff, don't worry. Let's take a break right here. And I will show you through examples. And I think you will feel a lot better that, oh, when I really have to hit the problems, the calculation is actually very simple. All right. And maybe toward the end, you'll understand what I am talking about even more. Okay. So don't worry about that. If you still sort of like 50-50, what are you doing? What are we doing? All right. So let's take a break right here. And after the break, I will take you to the distribution of point charges. And then I will show you how to calculate the potential from those charge distribution. And eventually, I will lead you to even the continuous case where you need some calculus to calculate. Sounds cool? All right. But I think by the end of today's lecture, you understand how to attack the potential problems for sure. All right, guys. So let's take a break right here, 10 minutes. And then I will sort of like attack all those problems and have you take a look at those. All right, guys, see you in 10 minutes. All right, guys, so I will show you how easy it is to apply this V equal to KQ over R. And after this, I think you'll have more confidence of how to do this calculation on your own. But let's first start from a very simple setup, and just to see the differences. Configuration, the different configuration can give you different final outcome. Okay, so let's start with this one. So when you have the arrangements, in this case, you say that you have 4 arrangements of charged particles are at the same distance from the origin. All right, so that's good. Now rank the situations according to the net electric potential at the origin. So every time that they talk about net electric potential, so this means there's not potential difference per se, but see, take the potential to be 0 at infinity. So it's a relative potential with respect to the infinite distance charge or distance that has 0 potential. There you go. All right. So by seeing this, you know that you will be able to use this KQ over R expression for your potential calculation. Sounds cool? All right. Now, and then when you have more than one charges over here, then what will you do? So the concept is simple. Just add them. Just sum them up. The good thing about this one is each one give you KQ over R. And this one is just a scalar quantity. So that means if you have more than one, all you need to do is just do an algebraic sum. You just sum them all. All right. So let's take a look at this one. Part A, you have plus 2Q and minus 9Q. So let's say that the distance over there, let's take it to be A. I will just, come up with that distance just like a parameter. So you can say that the net potential at A is start from the top, K, the charge generating that potential plus 2Q. See, now I bring in the positive sign into this calculation because potential is a scalar quantity. Positive and negative sign will give you different potential value divided by A. And that's it. That's for the first charge. Now you say, but John, I have another one, negative 9Q, just K, negative 9Q over A. So net, you get negative 7KQ over A, and you're done. That's it. Simple. Want to try again? Let's do part B. Now you have negative 2Q at the distance A, negative 3Q at the distance A as well. So it's going to be K, negative 2Q over A plus K, negative 3Q over A. You guys with me? So net, you get negative 5KQ over A, and you're done. Try again. Part C. Now you have 4 charges, but then 4, it's 4. That's fine. Go for it. Start from the top. K, negative 2Q over A. Let's go clockwise, shall we? So let's do negative Q on the right plus K, negative Q over A. They're all over A because they are at the same distance. Third one, K, negative 2Q over A. Last one, K, negative 2Q over A. So sum these all together, you get what? 1, 6, negative K, 7, KQ over A. All right, so I hope you start to feel at how easy it is to do the potential calculation here. Part D, give it a try. Same thing, just get used to it now. They are all separated from the location that we want to calculate potential equally. So it seems like at the end, you just do the K, and then you just sum all the Q and divide it by A. Does that make sense? They are at the same distance. So I can just take negative 4 plus 2, negative 7 plus 2. I get total of negative 7Q. That come from negative 4Q plus 2Q minus 7Q plus 2Q. Everything gets to negative 7Q. All right, and that's it. Those are the potential from these 4 arrangements. And which one give you the most positive? But this is good. So the answer is B. That's the most positive, so is the least negative among the 4. And the rest, the A, the C, and the D, they're all having the same potential at the origin. Done. Nice. All right, so we start to get the feeling of how easy it is to do. Actually, it's easier than it's easier than electric fields and force because those two, you had to do the vector. This one is just, all right, no, it's just purely numbers, just summing the numbers. All right, guys, try a bigger system here. So in the figure, 8 particles form a square. with distance d between adjacent particles. What is the electric potential at the center, point P? Let's say if the electric potential is 0 at infinity, right? See, this line comes in again, so that means it's qualify you to use KQ over R. That's good. All right, guys, go ahead. Let's start from the upper left corner, shall we? All right, so what we are going to do is we're going to take the potential from that negative 4Q at point P. So let me do this. The net potential at point P is going to be, start from the upper left corner, is going to be K, negative 4Q, divided by, now the distance, because they said this is D, this is D, this is going to be D root 2, right? From Pythagorean theorem. So it's going to be root 2D down here. Keep going. All right, move on to the negative Q. I will do in clockwise direction over here. So the potential from that negative 2Q on the top is going to give you K, negative 2Q over, now the distance is only D. Nice. Keep going. Now I get to the upper right corner. Positive Q is already at root 2D distance again. So I say plus K positive Q over root 2D. Keep going to the negative 5Q on the right. So I say K negative 5Q over D. Now you start to see why I classify this into two colors because I can see that I have 4 charges at 4 corners and I group them into one group because I know that the separation from the charge to point P, they are all the same, root 2D. And another group is the one at the center of each side. It's at the distance D from point P. So I just, separate them into 2 groups, one at the corner, one at the center of the side. So move on to the positive 4Q from the lower right corner. It's going to be K positive 4Q over root 2D. Get going. Down here, K negative 2Q over D. Keep going. Last corner charge is going to be K negative Q over root 2D. And the last charge at the center of the side is K positive 5Q over D. Done. And now all you need to do is just sum all these numbers together. Do we get lucky? It looks like it. These 2 cancel, that 2 cancel. So it looks like all those charges at the corner will generate 0 net potential at point P. What about the blue? The blue, these 2 cancel, and that's it. The rest of those 2 are not. So that's it. Negative 4KQ over D. And that's it. You like that? I think. So I hope it is easy to do the calculation because you don't have any directional problems to have to consider, right? Then there are no directions. It's just purely numbers. But then the only thing that you have to be careful with is you can have positive and negative potential. So the combination could be 0, right? That's all possible. Having fun here? Try again. All right, now your arrangement can be as weird as you like. Doesn't really matter. The only thing that you need to do is just do the KQ over R. If you did have this one, so you have a rectangular array of charged particles fixed in place. The distance is 50 degrees centimeter. That's the value of A. Charges are shown in integer multiple of Q1 and Q2, all right, which is now, all right, different values of Q, so that's fine. Take V to be 0 at infinity as usual. So that means that's good for us to use KQ over R. What is the net electric potential at the rectangle's center? So it's almost the same as the previous one, but it's just different geometry. So let me draw this line of sight, allow us to locate. So let me call that center point P again as usual. All right, and now let's see what can we do here. So now we can do things very quickly now. The reason I say we do that because by inspection, can you see that? If you look at the charges at the corner, they are at the same distance from point P, right? But then the net value of this charge, the summation of all those four charges added to 0. Do you notice that? It's a positive 2 Q1, negative 3, positive 2, negative 1. They added to 0. So that means you can say right away that the contribution from the corner's charges are 0. So what you can say is the net potential at point P comes from only those two charges at the top and the bottom. So it's going to be 2K positive 4Q2 over, all right, this is going to be A over 2. A over 2. That's it. Is it good? All right, and it's very quickly done to be what? For 16K Q2 over A. And you're done. All right, so this is a good sort of like examples for you to see that to manipulate or to calculate the net potential from arrangements of charges is very, very easy in the sense that we don't have to worry about directions anymore. So there's no components to break, there's no decomposition of vectors to come into play. Everything is so good. All right, it's nice. It's very nice. Okay, get going, guys. Now let's try something just like what we saw before. If it's not in the horizontal or vertical directions, it's not on an XY axis, it's just a free floating orientation here. In the figure, what is the net electric potential at point P due to these four particles? We did this in the electric field problems already. Let's do it under potential, shall we? All right, so what we want is to figure out the net potential at point P. So let's start from the upper left. Okay, let me call this like 1, 2, 3, 4, yeah, shall we? All right, so we can refer to each one very easily. So start from charge number 1. So I would say it's a K plus Q over D. Done. Charge number 2, K plus Q over D. Charge number 3, K minus Q over D. Charge number 4, K minus Q over 2D, right? That's the distance here, 2D. And that's it, guys. It's easy, right? It's super contrast with what happened in the first half of the lecture, right? It's just like, okay, Dad, why don't you just show me the formula and do this? All right, you need to understand it first. Okay. All right, over here, anything can be canceled. All right, I think this is good. All right, and you have KQ over 2D left. So the net potential is positive KQ over 2D, if my math is correct. All right, good. So far so good. Kind of like this. Yes, yes, yes. Okay, keep going. Now, Bojan, yeah, we did this, yeah, with the electric field before. Let's do it with potential, shall we? All right. So what if your charge distribution is now continuous? So you have a piece, like in this case, you have a ring of charge, and you would like to find the potential instead of electric fields at point P. The ring has a radius A. The distance of point P from the center of the ring perpendicular to the plane of the ring is X. Can you guess? Well, you don't need to guess. All right. So the way that I do this is, of course, you're just going to extend the summation into integral. Okay. And for those of you that are wondering about that, what is this 1 over 4 pi epsilon naught? Is don't worry about it. If you remember from last lecture, we said there's a constant over here, and the constant can be expressed into two ways. It's either in Coulomb constant K, or we're going to introduce another constant epsilon naught later. But anyway, the idea is you have some constant K in the front. Okay, so all you have to do for this one, for continuous case, is to just extend the summation into integral. So it means you have to do calculus a little bit. By what do? We slice that continuous piece of charge into a tiny piece first. Shump, shump. And let me call it, there is a charge in there, dq. All right. So let's consider just that dq alone. It will contribute the potential at point P to be equal to V at P is K the charge that doing the potential divided by the distance, which from the Pythagorean theorem is x squared plus a squared. And because this is a tiny, tiny, tiny amount of charge, you say this is going to be a tiny, tiny, tiny amount of potential at point P. Cool. But then what you do next is, John, I'm going to keep doing this dq, 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 dq around the ring. But then, as you can see, no matter where you cut this piece, the expression that you already set up still works. This expression can be used to describe the potential from any dq that coming out from this ring. Does that make sense? Yeah. All right. So you can use this expression for the blue dq, or you can use this expression for the green dq that you cut. They're all sharing the same thing. So that means all you need to do is just sum these. But when you sum it infinitely, many of that is the integral. Once you're done with this, that is your net potential at point P. Isn't that cool? All right. And with this, now let's proceed. Is it easy to do this integral? It's just like what we had back in the day of the electric field. Whatever constants, let's pull it out. K is good. X squared plus a squared is also good to pull out. What do you have left under the integral sign is a dq. And what is the sum of the dq? Just dq, 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 dq. When you sum them up, that's just the net charge on the ring, which already said it's just the capital Q. So that's it, guys. That's it. See? But then, of course, I approached this problem using a little bit of the calculus setup. But for those of you that are already familiar with all the previous problems, you probably have already noticed. But Ajahn, it's the same kind of problem. Point P is at the same distance to all the charges on this ring. No matter whatever piece of the charge on the ring that you are interested in, they are at the same distance from point P, which is square root x squared plus x plus a squared, right? So we already learned from the previous problems that as long as you stay at the same distance, all you need is just the sum of all those charges. So that's why I said, if you look at this one and just say, Ajahn, you know, the potential at point P is going to be K, the total charge of the ring over the distance from the P to the ring. That's it. You're done as well. All right. But at least we explain it using calculus. That's kind of nice. Doable? All right. If this is doable, guys, give me one more, shall we? All right. This one, I'll give it 2-minute head start, you guys. Maybe 2 minutes you're already done, I guess. I hope you should be done already. Oh, okay, sorry. Okay, you want previous slide again. Is that right, this one? Is it this one here? Okay, all right. Oh, one before this one? Yeah. Okay, all right, very good. All right, guys, try this. 2 minutes. What do you get? Well, you can guess that the problem that I present to you is not going to give you like headache in terms of like the mathematical complexity, right? It's just going to be just about you guys to throw up a little. All right, just, you know, just feel a little bit of like, okay, all right, I hate this, all right. All right, but stated, you know, stick with the concept and the procedure that we did. Okay, so when you have a continuous charge distribution, you slice this into a tiny piece first, and you say that tiny piece contains a tiny amount of charge dq. And now you start to see, but Ajahn, I got you here. Because once again, you have an arc, but whatever dq that you slice out from this arc is going to stay at the distance capital R from point P. Can you see now where things about to go here? All right. But anyway, I'm just going to set it up properly for you guys. So I can say a tiny potential at point P that come from that dq can be calculated by K, that tiny charge over R. And then what you're going to do is you're just going to do dq all the way to the bottom of the arc. Okay, but no matter dq that you slice out, so let me give you another example of dq in the green here. The expression that you have right there still works. It's still K dq over R anyway. So that means what you really need is just to sum all those throughout the arc. Once you integrate that, that will be your net potential at point P. Nice. All right. And then you can start doing this integral very easily by saying that K is constant, capital R is also constant. There's nothing to integrate because it's just a sum of all those dq. So that means it's just the total charge on that arc. And that is it. It's done. Believe it or not. See, lovely, right? It's much better than electric field calculation, right? Back in the day of the electric field, you have to do the components, the vertical component cancel. You only added the one that points horizontally before you do the integral, and then you have to take the cosine, and oh wow. But for the potential, done. Nothing else. Cool. All right. And you still notice that every problem still have to state this one. Take V to be 0 at infinity. So you will see this in all problems, and too bad. Just to make things proper, it's sort of like, you know, so it's physics that we're doing is not wrong. So we need that clause. We need that line right there. Okay, cool. So with that, let's finalize today's lecture with this, shall we? Okay. All right. So the reason I want to finalize today's lecture with this is just, well, not totally finalized, but I'm just gonna do a final conclusion in terms of the energy at the end. But in terms of the calculation, I think this is the one that I want to do to show you how to calculate the potential. All right. So in this figure, it's just an extension from this one. Let's say if you have 3 thin plastic rods, form quarter circles with common center of curvature at the origin. All right, so everything is good there. And now you have a uniform charges on the rods, Q1, Q2, and Q3 are given. What is the net potential at the origin? Can you sort of like see how to do this right away? Well, John, well, this is not bad because we just did this arc problem over here is as simple as K Q over R, where the Q is just a charge on that rod or the arc. Well, that over here is just like, okay, you have Q1 here with the radius 1, and you have Q2 here with the radius 2, and you have Q3 there with the radius 4. So all you have to do is just calculate the electric potential from each rod and sum them up, right? So the net V at the origin is going to be V, let me call V1, V2, and V3, shall we? Okay, and it's simple as KQ1 over 1 centimeter, 0.01 meter. That's from the first arc or the first rod inside, that's a Q1 rod. And then followed by KQ2 over the radius of the rod, which is 0.02 meter. And plus KQ3 over 0.00404. And that's it, guys. You are done. So that's nice. Okay, so that's what I'm trying to say, that, hey, by knowing the concept of the potential and understand that it's just a scalar quantities, the calculation is just simply adding numbers together. Okay. All right, so just to make things sort of like complete circle and everything. So once again, this potential calculation get rid of the test charge, We do things like we do energy, but per coulomb, correct? So now let me take everyone back to original concepts of energy that we discussed and what kind of relationship that you can get out of this potential and potential energy pair. Let's answer this one. So we'll come back to the original problem, potential energy. So if you already know how to calculate potential and you really want to calculate potential energy, what do? Yeah, you take the charge that you are considering and you multiply by the potential at that point. But then the thing is, I emphasize that potential at a point doesn't really exist in the sense that it's always comparing to something, right? And if you want to use KQ over R, you already take the comparison with V equal to 0 at infinity. You guys with me? So that means the very, very basic idea of using this KQ over R, and then you are about to attach the charge that you want to move. Okay, you guys slowly take along with me here. So if you have the Q2 and the Q that you have in your potential expression is coming from another charge Q1, you probably can say, well, John, all you need to do to get to the energy is multiply the Q2 due to the potential Q1, due to the Q1, right? That's our concept of getting back to the energy. But now you have to understand that this Q2 actually has to attach to this as well, right? Because that KQ over R expression means it implies 0 potential at infinity. So don't be afraid to say, if you use this expression KQ over R, you multiply the charge to that expression, it will be equivalent to saying that you want to move a charge from infinity, drag it to this point. Does that make sense to you? That is the amount of energy that required for you to bring in the charge Q2 from so far away and place it at the location of the potential KQ1 over R. Okay, start again, right? If you're still confused, think of it this way. Look at this figure over here. At first, you have Q1 waiting. You are interested in interested in what is going on at point P. You say, but Ajahn, potential at point P can be calculated very easily. Is it just K Q1 over the distance from Q1 to point P? Let's call it R12. So this one, check. You know how to calculate potential at point P due to charge Q1. But then I say, hey, I want to bring in the charge Q2 and put it there. I want to bring in the Q2 and place it at point P. How much work or how much energy do I need to supply to this Q2? Easy. I take Q2 and I just multiply by the V at that point and I'm done. Does that make sense to you? Yeah. Well, it has to be done because by definition, the potential is energy per unit charge. So now you know the amount of charge you want to bring is Q2. You just multiply it back. You get the amount of energy, right? But that it means is, imagine like you drag the Q2 from infinity, that is so far away, and drag it and just put it there. You need Q2 VP amount of energy to do that. And that is it. I hope you understand what does it mean by potential energy now. But the idea is kind of weird in the sense that if you want to use KQ over R, your reference is so far away, right? But if you use like MGH, which is the QED, is the one that you're doing on the surface of the earth. Your reference is pretty much like on the floor and you bring it up 1 meter. So your reference is just like nearby. But if you want to use KQ over R, your reference is just super far away, that's all. But it works, it's fine. In reality, you have to do that anyway, right? So why do we care so much about this? That's the question, Madan. Is it too much of the thing to discuss? But no, think about this. Imagine this. If this Q1 is electron, I mean, let's start by proton, let's say. If this Q1 is proton, and the Q2 that you bring in is an electron, see what you're doing? You are trying to generate like a hydrogen atoms, something like that. So that means for you to have a hydrogen atoms, the nucleus is proton, and there's an electron that's orbiting around. At least you need this much energy to have that hydrogen system in front of you. Does that make sense? All right. So to have a hydrogen atoms, it doesn't create hydrogen atom by itself. You just need to assemble that into a hydrogen atoms. And this is at least the way that you can come up with the idea of how much energy is required for you to build, well, you're not building it, but I mean, to construct a hydrogen atoms into an existence. That's what it is. Okay, cool. And now you start to imagine that, okay, if you want to extend a little bit further, for example, if you want to generate a more complex molecules, then you probably have to bring in more charges into your system. And then you have to keep doing this one by one, which make perfect sense. All those charges started out from so far away and started like bring it here, bring it here, bring it here. Okay, cool. When you say far away, it means it doesn't really have to be like infinitely far away. It just means that it's far enough that you don't get any influence from the electric field from the system that you have already had, something like that. Okay, all right. So that's the whole idea. So let's sort of like give you a better construction of this one. Okay, let me stop today's lecture with this slide. And once again, I just want to park this idea in your brain, in your head, and have you think about this one. And next time, I will start the lecture with more exercise of potential energy calculation. Sounds like a good plan? Okay, all right, try this one. So they say, find the work done in bringing 4 microcoulomb charge from far away to point P. Here, I want to have 4 microcoulomb, and I just I want to put it there. I intentionally write the path to be crazily weird because it's path independent anyway. So I can bring my 4 microcoulomb charge in any path I like. But eventually it's going to end at point P. How much energy do I need? Well, that's easy because all you care about is what is the potential at point P. So I want to figure out V at P. And V at P is very easily calculated. It's just K, start from 5 microcoulomb over 4. That's my first term here. Followed by negative 2 microcoulomb over 5. That's the second term there. With me, guys? That's how you calculate potential at point P. And the amount of work done that you have to put into your 4 microcoulomb charge is take that 4 microcoulomb charge, multiply by V at P, and that's it. You're done. Is that easy? All right, but the whole idea that I want you to think is this. Potential over here is 0. Potential at point P is this much. You feel anything now? You start from 0. You are going uphill. You start from 0. You want to go up to 7.65 times 10 to the third volts. You're going uphill. You're going into a higher potential. So that's why the work done has to be positive because you need to supply energy for you to walk uphill. That's the whole concept of potential. Must be the same as your potential energy in the day of the gravity. When you have a higher potential, that usually it means it's higher potential energy as well, right? So that means you're starting from 0. You want to walk uphill. to a higher positive. So you walk uphill to 7650 volts. So of course, to do that, you need some energy to bring yourself uphill. That amount of energy is this. So this is the reason why at the end it's still positive work done. Does that make sense? Okay. All right, guys. So I hope this introduced the concept of potential and potential energy to you. And I will just stop right here. And next time we'll do a little bit more of this to conclude the connections between potential energy and potential. And you will see the connections back to the electric fields. And I hope the whole concepts about the fields and the potential will be, complete then. All right, guys. So I hope you learned something today. And I think I'm still okay explaining things to you here. All right, guys. Take care. All right. Be safe. And I will see you guys. Well, just maybe just check the announcement a little bit. I might have a makeup coming this weekend, maybe just one at least. Yeah. So at least I can move the material forward a little bit sooner. Okay, sounds all right? Okay, guys. Thank you for sticking around, and I will see you guys soon. Okay, bye-bye. Thank you.